Thank you for the organizers for inviting me to give this ALD 101 tutorial. First, let's have a look at how the field has grown with time. Here is the number of doctoral theses on ALD as function of year made in different countries, collected in the virtual project on the history of ALD. You see how in the last years and decades, growth has been very fast, and the total number of theses is already more than 500 globally. ALD was invented twice, in 1960s under the name molecular layering, and in 1974 in Finland under the name atomic layer epitaxy. The Finnish work was directed to production of electroluminescent displays by ALD, and there the production started in 1985. In 1990, there was the first international conference on atomic layer epitaxy, where the name ALD also was introduced. There are some other milestones here marked, Intel announcing the use of ALD in high-K logic chips and the Millennium Technology Prize to Tuomo Suntola. There's also the paper by Alvaro and Yanguas-Gil characterizing the field. This tutorial will first present ALD in a nutshell. We'll talk a little bit more about the history of ALD and the two independent inventions, some more fundamental concepts, a separate section about growth kinetics and saturation profile analysis and conclusion. I have some terminology notes in purple and notes for caution in red for concepts where there are different views in the field, for example, or where the terminology is developing. This tutorial is largely based on a chapter we've been co-authoring with Ruud van Ommen and Aris Kulas for Kirk Ottmer Encyclopedia of Chemical Technology. ALD is based on repeated self-terminating reactions of at least two reactants on a solid surface. So you start from a surface which has some reactive sites. You bring in what is called reactant A that is able to react with those sites and leave behind a layer of adsorbed species. Then a purge or evacuation is done to remove the excess reactants and the possible gaseous byproducts so that you have a clean surface where the next reactant can be brought in, which reacts with that surface, again, potentially releasing gaseous byproducts. And once that is completed, then the surface is purged or evacuated again and be again reacted with reactant A. So you are repeating basically these steps where the amount adsorbed is increasing with time, and then you clean the surface in these purge or evacuation steps. Here is another view on the steps. So during an ALD process, the partial pressure of the reactants that the surface is experiencing is changing. You in an alternate way, you get the A and B reactants. The total pressure here is marked as constant, but that can also change. And here you see how the surface changes from one type to the other with cycles, and also the material accumulates in each cycle. Here you see what is the surface coverage plotted during 3 cycles and the mass adsorbed. So the surface coverage of these species on the outermost surface, it's switching between 0 to 1, corresponding to saturated surface, and then to 0 again when the next reactant comes, and so on, while the mass, and that's just switching between 1 and 0, while the mass accumulated increases in steps. You can also decrease in the step of reactant B if that's how those masses of the molecules dictate. And you can repeat this cycle as many times as you want to grow a layer as thick as you want. Many types of reactants are used. Here are some examples of them. They range from simple even elements up to complex metal organic compounds, and you have to be cautious. Sometimes these reactants are pyrophoric or toxic or otherwise harmful. Be careful and read the material safety data sheet. Some terminology. So I talk about reactants. Some others are going to talk about precursors, or they might mix these two terms, metal and non-metal precursor, or precursor and reactant, or precursor and counter-reactant, and so on. And also you might see, I'm sorry, there's one missing. Also some might call them reagents and maybe some other names even. And homoleptic, you'll see that refers to a compound where all the ligands are of the same kind, and heteroleptic has different types of ligands. So in this work, I talk about reactants, and that's what the atomic limits database also uses, but the other variants are also just as fine. But I would recommend to stay away from using co-reactant when you are talking of these two different reactants in ALD, because if you don't feed them at the same time, I don't think you should call them co-reactants. That refers to co-feeding. Further classification of ligands. Here is an example from a review a few years ago, classification to inorganic, metal organic, and further, well, alkyls, cyclopentadienyls, other alkoxides, beta diketonides, and so on. There are many classes, and well, you can have either elements or these simple halides bonded to a metal, or you can have organic groups, or you can have some heteroatoms that bond to the metal. So lots of development going on here and lots of variation. This you might have seen, it's the periodic table of ALD processes, where it's a summary of the processes existing to create a film of a certain element. So let's see, aluminium is there. So you see that aluminium metal has been grown by some special ALD process because of the gray background. And you also see that sulfides, oxides, nitrides, fluorides, and that's it. And some other compounds have been grown. So this summarizes a lot of things together. This work is being updated by TU Eindhoven, and everyone can propose additions, and you have to be careful or be aware that it might not be complete. So do your literature search anyhow. Non-metal reactants. In the conventional thermal ALD, hydrides of the nonmetals are really typical. In some energy-enhanced processes, such as plasma ALD, you can use molecules that would not be reactive enough, such as hydrogen or nitrogen or oxygen. So let's look closer. There's a lot of variation also here. So for example, trimethyl aluminium, reactant B for that. What can be made of trimethyl aluminium? Well, if you look at the database, you find aluminum oxide, aluminum sulfide, aluminum fluoride, aluminum nitride, and many, many different reactants that have been combined with this one metal reactant to make a film by ALD. Terminology question. In the trimethyl aluminium water process to grow aluminum oxide, is the water an oxygen source or an oxidant or oxidizer? Think of it. The correct answer is oxygen source. There's no redox reactions taking place. These oxidation states remain as in ligand, the same in the film. So caution, sometimes in ALD publications, people use the term oxidant or oxidizer even when there's no redox reactions taking place. So the right term would be an oxygen source in that case. ALD is based on gas-solid reactions, so therefore I see that it's a subset of chemical vapor deposition. The reactants can be at room temperature, solids, liquids, or gases alike, but then you have to vaporize them. Here is an example of thermogravimetric analysis for two ALD reactants from University of Helsinki. So in the curve 2, the reactant shows really nice clean vaporization, whereas in number 1, there is a weight remaining that tells that maybe this is not really suitable for ALD. Also, it would be nice if the reactants were not very expensive, not corrosive, and also not creative, not making reactive byproducts. The principles of ALD can be carried out in really different types of reactors. Temporal ALD is the most common. So there the substrate, the material to be coated, is stationary, and then these reactants are brought to the surface. So the partial pressures there are changing with time. Here are some examples of cross-flow, radial, different types of flow, also batch wafers or particle coating reactors, fixed or fluidized. Then you can also do spatial ALD where the substrate is moving or the sources are moving in a rotating carousel or even in a roll-to-roll way. So really many different ways, different reactor types can use the basic principles of ALD and create still the same film. What is really driving the growth of ALD, in my understanding, is the fact that the adsorption control leads to conformal films, meaning that if you have a difficult 3D structure in a surface, you can coat that inside these 3D structures also with the same kind of film as the outer surface. Here's a simple sketch to show that, and here's a little bit more realistic example of trenches on silicon where different ALD films have been grown, and so you see that beautiful conformal coverage by the film. And here are some examples from the semiconductor industry where ALD is being used, where the conformality is taken advantage of. Multiple patterning, 3D NAND, FinFETs, and there are many other applications where the conformality is important. Can we name a typical ALD process? Well, that's actually difficult, but I've tried. Temperature, we talk typically of some hundreds of centigrades. Pressure in the millibar range, but can be also high vacuum or even atmospheric. Growth per cycle, in any case, just a fraction of the solid bulk monolayer, but in the Ångström range, or if you want to talk about this areal number density, somebody has given a number of less than 5, and I think it's pretty good. Substrates, most often flat solids, but can be really different also. Most often temporal type, cycle time in the order of seconds, growth rate, so with time, something like 1 nanometer per minute, a slow growth technique. So this growth per cycle, it tells how much material is grown in an ALD cycle. It does not tell how fast an ALD process is. Sometimes in the ALD literature, people don't use just growth per cycle, but there's a growth rate added. The rate is there. This is mostly for historical reasons. People keep on using it because it has been done so earlier. I would like to say that it's a little bit misleading because this is not really a rate. It does not have a time dimension, and I do not recommend it, although I recognize that many still do use it. But you should be aware that this term growth rate can refer to two really different things in ALD. So it can refer to what is the growth per cycle, amount added per cycle, or the growth per time unit, for example, as in CVD. And in any case, you should be aware that this rate does not refer to a rate, as you would know in physical chemistry or chemical reaction engineering. If you assume that, then you are going in a wrong way. Also, word of caution, there is this term half reaction sometimes being used in the ALD literature. I thought it would be also good to mention here that I've also used it earlier, but I've come to the conclusion I don't use it anymore because all of these reactions, they are really full reactions. They are not like partial imaginary reactions like the half reactions in electrochemistry would be. So these are all full reactions. Half cycle is something physical that can, for my part, be used. Then about history, so molecular layering. Valentin Borisovich-Aleskovsky and Stanislav Ivanovich Kaltsov are the names associated to developing molecular layering since mid-1916s in St. Petersburg. There's a core concept called framework hypothesis by Valentin Aleskovsky earlier, and this is an image that kind of summarizes that. So a framework consisting of reactive sites where you can either add on those sites or remove them, and removing would lead to atomic layer etching. And that work was done much on powders. Here is a powder reactor, this big thing here, in 1982, but also on wafers and also for semiconductor applications. And this red part in the thesis description, that's all Russian work, so it has been massive. In 1974, Tuomo Suntola in Finland developed ALD. Here is a reconstruction of his first ALD reactor where elemental zinc and sulfur were used to grow zinc sulfide for the electroluminescent displays. Also other materials are needed there, but jumping to the prototype that is quite famous. So this flight display board at Helsinki-Vantaa Airport, which was hanging there from 83, I think 15 years further and working well all that time. Suntola got the Millennium Technology Prize for his pioneering work in 2018. Aleskovsky and Kautso have already passed away, both of them. There are some articles that have been written on the history of ALD. You can find the details here later. I will jump to this question. Is the history of ALD a difficult subject? I've heard people saying that. Well, it depends on whether you have thought or dealt with it, let's say. So the literature does not in general deal with this question in a good way. There are a few reviews on the history of ALD. I would recommend you to have a look at the early work on atomic layer deposition cited by Maligin and Smirnov, which really triggered me finding out more about the Russian side of ALD, which was not described in any of the reviews that I was aware of when I was a doctoral student and wrote my thesis. I found about those and summarized my findings in table 1 of a review I wrote and published in 2005. And maybe the fact that it is not fully treated subject in any case is that the review article by 10 high-level scientists or even leaders in the field, it received an erratum or correction just last year. Some say that the Russian works were not cited because they were all in Russian. Well, here is an example of a work in 1990 that was written in English in the conference proceedings of the first ALE conference where Viktor Drost participated. So that argument for sure is not correct, that it was only in Russian. There is the virtual project on the history of ALD going on. We have been finding out about the early works and we continue to do so. If you are interested, please have a look at the materials that you can find in the website vph-ald.com, and you can email this address if you would like to join. We are already 79 contributions from contributors from 20 countries. There is so much to find out about that nobody can do this alone, so it's good to join our forces and do this in an open science way. Then to the basics. So here is what the amount absorbed with time would look like in a reaction that is saturating and irreversible, and this is the core of the self-terminating reactions as I see it, or self-limiting as people see it. I would call this ideal ALD. There are other possibilities for amount absorbed versus time. If you don't have the saturation, you are in problems, you can't do ALD. If you have reversible reactions, you can't do ALD. If you have combination of saturating and not saturating, then, well, you are losing control. You can also have combinations of partly reversible and irreversible, either chemisorption or physisorption, and these you could still use in an ALD way, or if you don't provide enough reactant to the surface, then you also don't saturate. So many possible ways to deviate from this ideal ALD. Briefly on 3 monolayers that are relevant to ALD. Solid bulk monolayer, we already talked about this. Chemisorped monolayer after the reaction of reactant A or B or whatever. And then there's a reference case of physisorpted monolayer, not really active in ALD, but can be good as a reference for how much you can fit on a surface. So what's the characteristic dimension? Well, for the solid bulk monolayer, that's defined by the material that is being grown itself. For a Fisisop monolayer, that's defined by the Fisisop molecule, its size, whereas for the Chemisop monolayer, it's really defined through the surface primarily. And for chemisorption, there is no really simple way to calculate this for ALD. For Fisisorption, there is. If you know a radius of this molecule, then you can easily calculate how much you can fit in a hexagonal closed packing, and then you get the maximum theoretical amount absorbed. And for a solid, you can always take an average monolayer by considering the density and the molecular mass and calculating from that. Example, TMA trimetal aluminum water process has a growth per cycle of about 0.1 nanometers. So a solid bulk monolayer of aluminum oxide would have something like 0.3 nanometers. And this gives that the growth is about 30% of a monolayer per cycle. And that has been marked actually here in this cartoon showing the every third square as a blue one. Well, how about Chemisop monolayer? Actually, we do get a monolayer by definition. You remember the coverage going to 1 to 0 to 1 to 0 and so on. If you look at the amount of aluminum atoms adsorbed, it's something like 4 to 5 at typical ALD conditions. How about the Fisisop monolayer? Well, if you think of these ligands of the reactant, for methyl groups, we know that the van der Waals radius is about 0.2, and from that you can calculate the maximum theoretical ligand packing, and that would be about 7.2. We are at something like 70% of that, 5 to 6 methyl groups per square nanometer. Sounds pretty dense. Caution. So there is a widespread misassumption that ideal ALD should result in a 1 bulk monolayer per cycle. I think that this is not so at all. If you start going into details, it is very unlikely that you would ever grow 1 bulk monolayer per cycle. Where does this misassumption come from? Well, maybe mixing up the different definitions of a monolayer, because in Chemisorption you always make that monolayer, but still when you convert that to the bulk material, it's not a monolayer. And maybe also cartoons that illustrate ALD in a too simplistic way. If you look at the trends with growth per cycle with temperature, there are many possibilities. And in all of these possibilities, you still can fulfill this ideal ALD case where the amount absorbed increases and stabilizes to a constant after that. Also, if you look at growth versus cycles, so people call this the growth curve amount on the amount of material versus the number of cycles. Here you can also have many different trends still fulfilling that ideal ALD saturating and irreversible reactions. So when you start growing on one material, the amount chemisorbed in metal atoms per unit surface area, that can be very different for one case than for the substrate and the material that you're actually growing. So aluminum oxide starting on silicon, for example, and then ending on aluminum oxide, you can have these differences in the beginning before you settle to a constant value, and that's all normal. These are the 3 most commonly observed and discussed chemisorption mechanisms: ligand exchange, associative adsorption, or association in short, or dissociative adsorption, or dissociation in short. In ligand exchange, a gaseous byproduct is produced. Very often this is a hydrogen-terminated reaction, hydrogen-mediated reaction where, for example, in the case of trimethyl aluminum, a methane molecule is released. In other cases, other molecules, whereas in association and dissociation, nothing gets released, but everything, all the fragments are bonded to the surface. In the case of association as a whole, in the case of dissociation in different fragments. Saturation determining factors, number of sites can limit. So if you have a certain number of sites and you react with all of them and you can't react anymore, that would be one case. But you can also have lots of sites on the surface, but you can't access them because the chemisopt layer already blocks access to them. So then in that case, the steric hindrance would limit. You can have also a combination of these two. To my understanding, the trimethyl aluminium water process is behaving like the case C here. Growth modes are sometimes discussed. Two-dimensional growth or Frank van der Merwe growth is often even assumed for ALD, while I wouldn't actually see why we should exactly follow this. Then there is the theoretical case of random deposition in between before we go to the island growth or Volmer-Weber growth, where the growth preferentially occurs on the already deposited material. So here in the random deposition, you don't have any preference. In the first case, you always deposit in the lowest available row of material in a way. Area selective ALD takes advantage of the fact that the reactivities of different types of surfaces for a certain molecule are different. So you need those reactive sites to enable the growth. And if you don't have any, then you don't grow. So you can grow in part of the material and not in others. You can do this by blocking part of the surface, or you can do this by using the fact that you have this certain type of growth curve and a very low growth per cycle in the beginning, and sometimes you do back at the edge to have the surface clean. All right, deviations from ideality. So ALD window is a concept developed by Suntola. This is his main review, Materials Science Reports, 1989, where he presented it in full. And I'll use this as a reference as well. So deviations from this ideal way of amount absorbed versus time. If you have multi-layer physisorption, then you are getting more material, slow reactions with insufficient reaction time. You are staying in this lower level of amount absorbed. Thermal reactant decomposition would give you a continuously growing component, or desorption. You would start to desorb here during the purge. What is not shown in the figure, but what can also take place, is overlapping reactant pulses. And this is a really important engineering aspect for ALD reactions, how to keep those quick reactions separate. You can also have competitive adsorption of gaseous byproducts or etching, or sometimes even subsurface processes where the partial pressure of your reactant starts to affect. It should not ideally affect if you have irreversible reactions. Growth kinetics and saturation profile analysis. Langmuir adsorption is a simple concept that is used to model ALD. Associative adsorption on a single site in a reversible way originally, where all the surface sites are equal, flat surface isothermal conditions, no interaction between the species, and adsorption and desorption are elementary processes. Many of these assumptions are actually not fully valid, but they are typically assumed, and not only in ALD, but also CVD and catalysis. Real ALD processes are complex, but still it's often sufficient to use this simplification. So here's the simple Langmuir adsorption. Here is a real case. You might have ligand exchange, association, dissociation, also adsorbate interactions. So not so simple, but still modeled in the simple way. Actually, this saturation curve, amount adsorbed versus time, this has been produced with this surface coverage with time that you can get when you solve the Langmuir adsorption equation as a function of time. A warning, don't mix up this concept with Langmuir adsorption isotherm. It has been mixed up in the field of ALD. The shapes can look a little bit similar, but this isotherm refers to equilibrium pressure, whereas the saturation curve has time on the x-axis. There's a separate presentation about that mix-up given last year. When you carry out ALD growth in a narrow channel, be it a specific test structure like depicted here, or in a reactor where the reactants flow, you can observe the film termination profile, the thickness profile, saturation profile, and extract kinetic information from that. Here it's shown how with increasing dose, the saturated area, so the film grown here, it's extending deeper as function of distance. And from the shape of this, you can back calculate kinetic information, so sticking probability or sticking coefficient. Arts et al. Has developed what is called the slope method, where from just measuring here the slope with a simple formula, you can calculate the sticking coefficient, provided that the growth is in Knudsen flow regime, meaning that there are no gas phase collisions, but that the molecules collide on the walls, basically only. Well, if you want to then go to deeper modeling, you have to describe the adsorption rate and the mass transfer rate. Here is how the adsorption rate is described in two different papers. This might look a little bit different, but basically if you go to the fundamentals, they are the same. You always have the surface coverage, fraction of empty sites. Here, the definitions were a little bit different. There is the lumped sticking coefficient, that is the fundamental thing. It tells how many hits on the surface lead to adsorption. So if you have sticking coefficient of 0.01, then of 100 bumps on a surface, one leads to reaction. Partial pressure of reactant A, temperature, molar mass, and also something that is related to growth per cycle. They are all included here. Diffusion equation, Fick's law, from two different papers. These also might look different, but if you go really in the details, they are fundamentally the same. I can't go in details now. Recently, test structures have been made available where you can measure these saturation profiles or thickness profiles inside narrow channels. There are websites to find more information of that, and also a presentation to come. And there's also open code, which you can yourself also use to simulate these conformality or the thickness profiles in GitHub called MacBall, and this is valid for, again, for Knudsen flow regime. Last warning, so extracting kinetic parameters for ALD has been difficult because ALD reactions are so fast, but now it's possible through this slope analysis. And if you get an expression for the reaction rate constant, then as function of temperature, then you can do the Arrhenius plot and find the adsorption activation energy. Here is an example where that has been elegantly done. And then word of caution, here don't mix the growth per cycle with a growth rate. For this, you can't do that analysis because this is not a kinetic parameter. I've seen it being done in the ALD field and also atomic layer etching. Don't do it. This is not a rate. Do it for the sticking coefficient or another kinetic expression. So we've covered ALD in a nutshell, fundamental concepts, kinetics, history. You can find more in the openlearning.aalto.fi site, which is being built in international collaboration. Thanks a lot for your attention.